Now we are going to analyze the filters by using Butterworth filters as well as by using Chebyshev filters, by using Kauser filters. We can analyze the filters. Now first I am going to consider the Butterworth filter. By using the Butterworth filter, first I am going to realize the first order low pass filter. So the RC network along with the op-amp is used in the non-inverting configuration, will be used as a first order low pass Butterworth filter. Okay, first I want to calculate the gain from this circuit. How can you calculate the gain? We all know that this circuit will be nothing but the non-inverting op-amp. Why we are treating it as a non-inverting op-amp is we are applying the input at the non-inverting input terminal, and the value of VA, that means first we have to calculate the potential at VA. VA will be calculated with the help of R, C and Vin, and the reactance of the capacitance will be taken as XC will be equal to 1 by 2 pi into FC. That will be nothing but the reactance of the capacitance. First I want to calculate the potential at A. VA will be equal to, using voltage divider rule, we are going to calculate the voltage at node A, and VA will be equal to Vin into minus JXC divided by R minus J into XC. Just now I told you that the capacitance reactance will be taken as XC, that we are going to be considered here as 1 by 2 pi F into C. So substitute that value. XC will be equal to 1 by 2 pi F into C, and minus J will be treated as 1 by J. Okay, so the equation will becomes VA will be equal to Vin divided by 2 pi J into 2 pi F into C divided by R plus 1 by J into 2 pi F into C. From this, VA will be represented as Vin divided by J into 2 pi F R C plus 1 divided by J into 2 pi F C. There in the numerator also we are having J into 2 pi F C. Both will be cancelled together. Finally we are getting the voltage at node A will be treated as VA is equal to Vin divided by J into 2 pi F into RC plus 1. And for the low pass filters, we are going to assume the higher cutoff frequencies. So I am assuming higher cutoff frequency FH will be equal to 1 by 2 pi into RC. Substitute this FH value in the above equation, then you will get VA will be equal to Vin divided by 1 plus J into F by FH, where FH is nothing but the cutoff frequency, and which will be also taken as corner frequency, or it is also taken as 3 dB frequency. Okay, now which is the value of VA, that is Vin divided by 1 plus J into F by FH, and we all know that the output voltage of the non-inverting amplifier will be equal to 1 plus RF divided by R1 into VA. So output voltage is equal to 1 plus RF divided by R1 into VA. So from this substitute VA value in this equation, then we will get 1 plus RF by R1 into Vin divided by 1 plus J into F by FH. Okay, so from this what we are going to calculate is V0 divided by Vin will be taken as 1 plus RF divided by R1 divided by 1 plus J into F divided by FH. 1 plus RF divided by R1 will be taken as gain, so which will be taken as AF divided by 1 plus J into F by FH. okay, which is nothing but the gain of the first order low pass filter, that is AF divided by 1 plus J into F by FH, where FH is the cutoff frequency and F is nothing but the operating frequency. By proper selection of the values of F, we are going to draw the frequency response curve by using the magnitude value from the transfer function, or which is also called as gain. Okay, so from this, what is the value of the gain? Modulus of V naught by V in will be equal to AF divided by square root of 1 plus F by FH square, okay, which is nothing but the magnitude. And we can also calculate the angle, phase angle. Phi is equal to minus of tan inverse F by FH. From this gain, we can draw the frequency response easily. Here I am going to represent the frequency response curve for the first order low pass Butterworth filter. Here we are going to take it as gain in dB, and here I am going to consider the frequency. So first tell me what happened when at F is equal to lower frequencies and when at F is equal to FH and when F is greater than FH. I want the values of gain. From that we can easily draw the frequency response curve. Suppose case 1 is when F is less than FH. So what happened? When F is less than FH, then we will be neglect the term F by FH. Yes or no? So we will get the gain or magnitude value will be taken as V naught of divided by V in will be taken as AF. That means for less than cutoff frequencies, the gain will be constant, which is nothing but AF. Case 2. What happened when F is equal to FH? Okay, when at F is equal to FH, then we will get AF divided by square root of 1 plus 1. Okay, that is nothing but AF divided by square root of 2. That means we are going to get the gain will be equal to 0.707 into AF. Exact at the cutoff frequency, the gain will become 0.707 into AF. And last but not the least is case 3. What happened when F is greater than FH? When F is greater than FH, so what happened in this case is we will get the less value than the gain. That means the gain will be decreases from the higher gain to the 0. Okay, so what happened is when F is greater than FH, then we will get the less value than the gain at F is equal to 0. That means the gain will start reduction after the cutoff frequency, and at a particular frequency the gain will become 0, which is nothing but the first order low pass Butterworth filter. Now I am going to draw the frequency response curve by using all those 3 cases. At F is equal to 0, the gain will be equal to AF, and until the cutoff frequency FH, okay, the gain will be same. Once it reaches the cutoff frequency, the gain will be decreases to 0.707 into AF. Okay, now after the cutoff frequency, the gain will be decreases, and at a particular frequency it becomes 0, which is nothing but the frequency response of first order low pass filter. In the first order low pass filter, the gain rolls off by minus 20 dB per decade. In the problems, whenever they are asking us to design the first order low pass Butterworth filter, then you have to use the following steps. Design steps. Step 1. Choose the cutoff frequency from the given frequencies. FH will be equal to 1 by 2 pi into RC. In the problem itself, they will give the cutoff frequency. So you have to take that as FH. And step 2 is choose the value of C. Always the value of C will be equal to or less than 1 microfarad. And from this FH and C value, then we can easily calculate the value of R. Step 3, by using the formula FH, we can easily calculate the value of R. Okay, and last but one step, step 4 will be taken as the gain of the low pass filter is decided by the resistances of RF and R1. Once in the problem they have given the value of AF, then we all know that AF is equal to 1 plus RF divided by R1. Okay, so RF by R1 will be equal to AF minus 1. From this, RF is equal to AF minus 1 into R1. By proper selection of value of R1, then we can easily calculate the value of RF. Okay, this is the way we are going to solve the problem for the first order low pass Butterworth filter. All these steps are required while you are going to solve the problem. After solving the problem, you have to draw the low pass Butterworth filter also. If they are asking us to design the first order low pass Butterworth filter, then you have to draw this first order low pass Butterworth filter. Sometimes they ask you to draw the frequency response also. Then you have to use the formula is modulus of V0 by Vin will be equal to AF divided by square root of 1 plus F by FH square. Yes or no? By using this, you can draw the frequency response, and you all know that for the first order low pass filter, the frequency response should be like this. So you have to find out the gain values. Okay, by using that table, you can draw the frequency response. Before going to explain the first order high pass Butterworth filter, I want to tell you about a important definition regarding to the filters. That is frequency scaling. Okay, once the filter is designed, sometimes it is necessary to change the cutoff frequencies of the filter. For changing the cutoff frequencies of the filter from the original cutoff frequency to the new cutoff frequency, this process is called as frequency scaling. It is important question for the 2 marks. Okay, now coming to the first order high pass Butterworth filter. If you observe the circuit of the first order high pass Butterworth filter, okay, which will be same as is that of first order low pass Butterworth filter, but there is a small change. Just we are changing the positions of R and C. Okay, from remaining thing is same as is that of what we have seen it for the first order low pass Butterworth filter. Here also I am going to analyze the first order high pass Butterworth filter by using this circuit. So here by using the C and R along with op amp used in the non-inverting op amp configuration, we are going to analyze the first order high pass Butterworth filter. First, you want to calculate the value of potential at A. Okay, so VA is equal to, by using voltage divider rule, okay, VA is equal to Vin into R divided by R minus J into XC, and we all know the reactance of the capacitance. XC is equal to 1 by 2 pi F into C, and minus J is equal to 1 by J. Same thing I explained for the first order low pass Butterworth filter also. XC is equal to 1 by 2 pi F into C. Substitute these values in this above equation, then you will get VA is equal to V in into R divided by R plus 1 by J into 2 pi F into C, which will be taken as V in into R divided by R into J into 2 pi F into C plus 1 divided by J into 2 pi F into C, which will be rewrite as V in into R into J into 2 pi F into C divided by 1 plus J into 2 pi F into R into C. Okay, for the high pass filters we have to assume the lower cutoff frequencies. Assume FL will be equal to 1 by 2 pi into R into C. So from this VA will be equal to V in into R into J into F by FL divided by F by FL divided by 1 plus J into F by FL, which is nothing but the potential at node A. Once we know the potential at node A, according to the non-inverting op-amp configuration, what is the output voltage? V0 will be equal to 1 plus RF by R1 into VA. So substitute the value of VA in this expression, then you will get it as 1 plus RF by R1 into V in J F divided by FL divided by 1 plus J into F by FL. So V0 by V in is equal to 1 plus RF by R1 will be taken as AF into J into F by FL divided by 1 plus J into F by FL, which is nothing but the transfer function of first order high pass Butterworth filter. Okay, so if you want to express the transfer function in the polar form, then you have to represent in the magnitude into phase angle. So in the polar form, that is modulus of V0 by V in and phase angle phi, which is nothing but the representation of the transfer function in the polar form. Now first I am going to calculate modulus of V0 by V in. Modulus of V0 by V in is equal to AF into square root of F by FL whole square. Then we will get F by FL divided by square root of 1 plus F by FL square. Okay, which is nothing but the magnitude or gain of the transfer function. Okay, so first see this one. What happened when F is equal to FL? Sorry, case 1. What happened when F is less than FL? When F is less than FL, what happened is we will get modulus of V0 by V in is less than AF. Yes or no? F is less than FL. So we will get AF divided by AF into F by FL divided by square root of 1 plus F by FL. So obviously F is a less value, F by FL is a high value we will get in the denominator. So obviously we will get modulus of V0 by V in is less than AF. What happened? Case 2, when F is equal to FL. So modulus of V0 by V in is equal to AF divided by square root of 2. So which is nothing but 0.707 into AF. And last but not the least, case 3. Case 3 is what happened when F is greater than FL. When F is greater than FL, if you comparing with 1, then that term will be neglected. So you will get it as modulus of V naught by V in is equal to AF into F divided by FL divided by square root of F by FL square. Square and root cancel, FL cancel, then you will get it as AF. So from these three cases, we can easily represent the frequency response. Okay, so in the frequency response, we are representing in gain versus frequency. At the lower frequencies, the gain will be 0. Okay, until the cutoff frequency, it will be slowly increasing, and at the cutoff frequency, it will be equal to 0.707 into AF. Once after the cutoff frequencies, it maintains constant, which is equal to AF. Okay, this is nothing but the frequency response of first order high pass Butterworth filter. Okay, similarly, what we have seen it for the design steps in the first order low pass Butterworth filter, here also whenever they are asking you to design the first order high pass Butterworth filter, you have to follow the rules what you have followed in the design steps for the first order low pass Butterworth filter. Okay, the design steps for the first order high pass Butterworth filter. Whatever the design steps we have used for the first order low pass Butterworth filter, the same design steps here also we are going to use for the first order high pass Butterworth filter. Step 1. Choose the lower cutoff frequency FL. We all know that FL is equal to 1 by 2 pi into R into C. From the given problem, choose the cutoff frequency. They will give that may be 100 kilohertz, that may be 100 hertz, that may be 10 hertz, whatever it may be. Okay, choose that value FL. Okay, next coming to the step 2. Choose the value of C, which is always less than or equal to 1 microfarad. Okay, from that we can easily calculate the value of R. Okay, FL is equal to 1 by 2 pi into R into C. From this R is equal to 1 by 2 pi into FL into C. Then you can easily calculate the value of R. Butterworth filter also, the pass band gain is depends upon the values of resistance RF and R1. So step 4 will be nothing but gain AF will be equal to 1 plus RF by R1. In the problem they will give you the gain. From that we have to calculate the values of RF and R1. RF by R1 is equal to AF minus 1, and from this R1 will be equal to RF will be equal to AF minus 1 into R1. Once choose the value of R1, then you can easily calculate the value of RF. Sometimes they asked us to draw the frequency response also. Then you have to use the formula is modulus of V naught by V in will be equal to AF into F by FL divided by square root of 1 plus F by FL square. Okay, where FL is the cutoff frequency or break frequency, and F is nothing but the operating frequency. Okay, by using this formula you can easily calculate the gain value. Once you know the value of gain for the different operating frequencies, then we can easily draw the frequency response, and you have to draw the circuit diagram also in the problems. To the second order low pass Butterworth filter, if you observe the circuit diagram with the first order low pass Butterworth filter, just here we are adding an additional RC network to the circuit, then it becomes the second order low pass Butterworth filter. In the first order low pass Butterworth filter, the gain rolls off by minus 20 dB per decade in the stop band, whereas in case of the second order low pass Butterworth filter, the gain will rolls off by minus 40 dB per decade. Whenever the order of the function will be increases, then the gain rolls off very fast when compared with the lesser order of the functions. So here I am considering the second order low pass Butterworth filter. Okay, for the deriving of the cutoff frequency in the second order low pass Butterworth filter, first I am going to consider the input RC network, and by applying the Laplace transform for the input RC network, I can easily calculate the cutoff frequency or output voltage of the second order low pass Butterworth filter. So considering first the input RC network, here it is Vin, and the resistance will be taken as R2, and here the resistance is R3, and here that is C2, and which will be connected to the output voltage V0, and here I am going to take it as C3, which will be connected to ground. From this it will be applied to the input of non-inverting op-amp. Drive the cutoff frequency for the second order low pass Butterworth filter. First we have to consider the input RC network, apply Laplace transform for this network, then we can easily calculate the cutoff frequency. Here we are treating it as V in of S, and here it is taken as 1 by S into C2, and here it will be taken as V0 of S, and here it will be considered as 1 by S into C3, and take this node as V1. Okay, and the current will be passing as I1 of S, and it will be dividing into I2 of S into I3 of S at the node V1. Okay, now so to calculate the cutoff frequency, what we are going to do is apply KCL at node V1. So what happened? Apply KCL. So we will get it as I1 will be equal to I2 plus I3. What is I1? I1 will be nothing but V in minus V1 divided by R2 will be equal to what is I2? V1 minus V0 divided by 1 by S into C2 plus V1 minus VA divided by R3. Okay, so V1, then we will get the expression as like this. So what we want to require is for the calculation of output voltage for the second order low pass Butterworth filter, first of all we have to calculate the voltage at node A. Once we know the value of voltage at node A, then it is easily to calculate, that is V0 is equal to 1 plus RF by R1 into VA. So from this expression, first of all I want to calculate the voltage at node A. So what I am going to do is from this circuit, okay, what is the value at node A? VA is equal to apply voltage divider rule, V1 into 1 by SC3 divided by R3 plus 1 by SC3. Okay, so now we can calculate it as VA is equal to V1 divided by 1 plus R3 SC3. Here SC3 cancel. From this we can easily write the value of V1. V1 is equal to VA into 1 plus S into R3 into C3. Substitute the equation 2 in equation 1. So what happened? This is V in minus VA into 1 plus S into R3 into C3 divided by R2 will be equal to V1 means VA into 1 plus S into R3 into C3 minus V0 divided by 1 by SC2, and then plus V1 is VA into 1 plus S into R3 C3 minus VA divided by R3. Now what you want to do is write VA terms as one side and remaining terms as another side. Then you will get it as V in. Here minus V naught by 1 by SC to take this side, V in plus V naught V in by R2. V naught by 1 by SC2 is equal to VA into 1 plus S R3C3 divided by 1 by SC2 plus VA into 1 plus S R3C3 divided by R2 and then plus take VA as common, 1 plus S into R3C3 minus 1 divided by R3. Sir, no. So now V in divided by R2 plus V naught into SC2 will be represented as, take VA as common. If you have taken VA as common, then it will becomes SC2 into 1 plus S into R3C3 and then plus 1 plus S into R3C3 divided by R2 and then plus 1 cancel, then you will get it as 1 S R3C3 by R3. Yes or no? So from this you can rewrite it as VA, take LCM as R2 R3, then you will get it as SC2 R2 R3 and then plus S square C2 R3 C3 R2 R3, so R3 square and then plus, here you are not having R3, so R3 plus S into R3 C3 R3 plus S into R3 C3 R2. Yes or no? LCM as R2, then you will get it as V in plus V naught SC2 into R2. Take R2 is cancel. Then what you want to do is you want the value of VA. So what you want to do is bring back this term as this side, then you can easily get the value of VA. Once again write down this equation here, V in plus V naught SC2 into R2 will be equal to VA. Now take S square terms as 1 and S terms as 1 and constant terms as 1. So from this expression, S square C2 R3 square C3 R2. So this S square term is over. Now in these three terms we are having S. So take down common as S. S into what we will get? R3 R2 C2 and then this is over and then next plus R3 square C3 R3 square C3, this is also over. So plus R3 R2 C3, so this is also over. Finally we will get the constant term as R3 and whole divided by R3. So if you observe this expression, each and every term consists of R3. So take common as R3, then you will get it as VA into R3, which is S square C2 R3 C3 R2 plus S into R2 C2 plus R3 C3 plus R2 C3 and then plus 1 divided by R3. So R3 has cancelled. So what you will get is VA will be rewrite as V in plus V naught S C2 R2 divided by the whole thing you are going to represent here, which is nothing but S square C2 R3 C3 R2 plus S into R2 C2 plus R3 C3 plus R2 C3 and then plus 1, okay, which is nothing but the value of VA. From this value of VA, then you can easily calculate the output voltage of second order low pass Butterworth filter. Now the output voltage V0 will be equal to 1 plus RF divided by R1 into VA. VA is nothing but substitute that value, so we will get it as AF into Vin plus V0 SC2 R2 divided by S square C2 C3 R3 R2 plus S into R2 C2 plus R3 C3 plus R2 C3 plus 1. Okay, this is the thing we will get once we will substitute in this expression. Now what happened is V0, take V0 terms as one side and V in terms as another side. So you will get it as V0 minus V0 SC2 R2 divided by whole thing you will get, that is S square C2 C3 R3 R2 plus S into R2 C2 plus R3 C3 plus R2 C3 plus 1 is equal to, here you are having AF also, so AF is equal to, so VA terms V0 terms brings one side and then finally we will get Vin into AF divided by the whole thing once again you have to write here S square C2 C3 R3 R2 plus S into R2 C2 plus R3 C3 plus R2 C3 plus 1. Okay. Take V0 terms as one side and V in terms as another side. From this I am going to take common as V0. Once you have taken V0 as common, then you will get it as 1 minus S C2 R2 into AF divided by, you will get it as S square C2 C3 R3 R2 plus S into R2 C2 plus R3 C3 plus R2 C3 plus 1 will be equal to Vin into AF divided by the whole thing once again you have to represent here S square C2 C3 R3 plus S into R2 C2 plus R3 C3 plus R2 C3 plus 1. Once again, please observe all the equations. I clearly represented all the equations while I am taking the common also. I have clearly represented all the equation. So please go through all the equations once again. Then we will go the remaining steps. Okay. Now I am moving on to the remaining steps. That means we want to calculate the gain as well as cutoff frequency. V0, take LCM, then you will get S square C2 C3 R3 R2 plus S into R2 C2 plus R3 C3 plus R2 C3 plus 1 minus S into C2 R2 into AF whole divided by, you will get it as S square C2 C3 R3 R2 plus S into R2 C2 plus R3 C3 plus R2 C3 plus 1 will be equal to V in into AF divided by the whole thing you will get, that is S square C2 C3 R3 R2 plus S into R2 C2 plus R3 C3 plus R2 C3 plus 1. This and this will be cancelled, then you will get it as V0 by V in will be equal to AF divided by S square C2 C3 R3 R2 plus S into, okay, if you have taken common, then S into R2 C2 plus R3 C3 plus R2 C3 minus C2 R2 into AF plus 1. This is the function of second order low pass Butterworth filter. So here what I am going to do is for the calculation purpose I am treating R3 is equal to R2 is equal to R and C2 is equal to C3 is equal to C. Then what we will get it as V0 by V in will be equal to AF divided by, and I am taking common also, then here under R square. Why? Because here I am taking it as C2 is equal to C3 and then R2 is equal to R3. So that means this term will be represented as C square into R square. Okay, so S square plus S into, here you are having RC, 3RC divided by, what you will get here it as square into R square. Yes or no? So finally V0 divided by V in will be equal to AF divided by S square plus, take RC as common, so you will get it as S into 3 minus AF divided by R into C plus 1 divided by R square into C square. Yes or no? Which is nothing but the gain of the second order Butterworth filter. Once you clearly understand the second order low pass Butterworth filter, then you can clearly write the second order high pass Butterworth filter. So we calculated the transfer function. From this we can easily calculate the cutoff frequency as well as we can easily calculate the gain value. Okay, this is the second order second order expression. Why I am treating it as a second order means here if you observe the order of the expression, the highest power of S will be nothing but 2. That's why we are treating it as a second order function. The standard form of transfer function of second order system is, it is V0 by V in is equal to A by S square plus 2 zeta omega n into S plus omega n square. Okay, and we are getting the transfer function is like this for the second order low pass Butterworth filter. Comparing these two expressions, then the A will be represented as overall gain, G is the damping factor of the system, and omega n is nothing but the natural frequency. Okay, so natural frequency of oscillations. So if you compare these two equations, then you will get it as omega n square is equal to 1 by R2 R3 C2 and C3. Why? Because R square is equal to R2 R3, C square is equal to C2 C3. Omega n is nothing but 2 pi into FH square, whole square will be equal to 1 by R2 R3 and C2 C3. From this FH will be equal to, what happened for FH? 1 divided by 2 pi into square root of R2, R3 and C2 and C3. So if you have taken R2 is equal to R3 and C2 is equal to C3, then you will get it as FH is equal to 1 by 2 pi into RC, which is nothing but the higher cutoff frequency for the second order low pass Butterworth filter. Okay, and next compare the middle term. So 2 zeta is equal to, why? Because here omega n is equal to 1 by RC. Okay, so S will be same, and 2 zeta is equal to 3 minus AF. From this we can easily calculate the damping factor, 3 minus AF divided by 2, which is nothing but the damping factor. And if you are substituting S is equal to j omega in this expression, then you will get the overall transfer function V0 by Vin is equal to AF gain. Overall gain for the equation is 1 plus F divided by FH whole to the power of 4, which is nothing but the overall gain of the given transfer function once you substitute S is equal to j omega. Okay, so if you observe this, here we are getting it as 4, and for the first order filter here we are getting it as 2. So now what I am going to do is same what we have written for the frequency response for the first order filter. Here also I am going to draw the frequency response for the second order filter also. So what happened, until the cutoff frequency FH, the gain will be constant. Once it reaches the cutoff frequency, then it will decrease as to 3 dB, which is nothing but 0.707 into AF. Okay, and after that the gain will be decreases and it will be touches to the 0 dB at the maximum frequency, and here the gain rolls off by minus 40 dB per decade. Why? Because here it is the second order Butterworth filter. And see this one, same thing what we have written in the case of low pass filter for the first order. Here also you have to calculate the same 3 cases. What is case 1? Case 1 is when F is less than FH. When F is less than FH, then what happened is modulus of V0 by Vin will be equal to AF. Why? Because this is neglected, then AF divided by square root of 1, then we will get it as AF. Then what happened for the case 2? Case 2 is when F is equal to FH, then you will get it as modulus of V0 by Vin is equal to 0.707 into AF. And last but not the least is case 3. Case 3 is equal to when F is greater than FH, then you will get modulus of V0 by Vin is less than AF. Okay, these are the values we will get for the different frequencies. From these values we can draw the frequency response of second order low pass Butterworth filter. Once you know the second order low pass Butterworth filter analysis clearly, then you can clearly explain the second order high pass Butterworth filter. Second order high pass Butterworth filter. This is the circuit we are going to be used for analysis of the second order high pass Butterworth filter. If you observe the circuit for the second order low pass Butterworth filter, just we are exchanging the resistors and capacitors, and remaining thing is same as it is that of what we have seen it in the second order low pass Butterworth filter, and same procedure you have to use for the calculation of the transfer function which we have used in the second order low pass Butterworth filter. Then you will get the transfer function as AF into S square by S square plus 3 minus AF into omega L into S plus omega L square. If you clearly understand the operation of second order low pass Butterworth filter, then it is similar to that of previous thing. So from this we can rewrite it as H of S is equal to S square as common, then you will get it as 1 plus 3 minus AF into omega L divided by S plus omega L divided by S whole square, and omega L is nothing but 2 pi into FL. There omega is equal to 2 pi into FL. Okay, substitute S is equal to J omega, then you will get the final transfer function that will be equal to AF divided by square root of 1 plus FL by F whole to the power of 4. Okay, so by using this transfer function, which is also taken as gain, we can easily calculate the frequency response. Until the cutoff frequency, the gain will be low value practically, but whereas in case of ideal it will be 0. Once it reaches the cutoff frequencies, then it will be allow all the frequencies. That means here it is taken as a stop band and here it is taken as pass band. Always the stop band and the pass band will be differentiated with respect to FL. That means separated by FL. The design steps. For the second order low pass Butterworth filter as well as for the second order high pass Butterworth filter. That's why here it has high pass slash low pass. Okay, step 1, choose cutoff frequency. For the low pass we will be taken it as FH. For the high pass we will be taken it as FL. That is 1 divided by 2 pi into square root of R2, R3, C2 and C3. But easy simplification purpose, we are assuming R2 is equal to R3 and C2 is equal to C3. Then we will get it as 1 by 2 pi into RC. And same for here also, FL is equal to 1 by 2 pi into square root of R2, R3 into C2 into C3. Here also the same procedure, you have to use what you have chosen for FH. So we will get it as 2 pi into R into C. And coming to the step 2, choose the value of C will be equal to 0.01 microfarad. Once you know the value of C and you know the value of FH or FL, then you can easily calculate the value of R. Yes or no? That is R is equal to 1 divided by FH into 2 pi into C, or R is equal to 1 divided by 2 pi into FL into C. Okay, next coming to the step 4. Okay, for the first order low pass Butterworth filter, the calculation of RF and R1 values, you require the gain for the first order low pass Butterworth filter. But whereas in this case, the gain is, if you observe the second order Butterworth polynomial equation, which is nothing but S square plus square root of 2 into S plus 1. So the middle term in our expression is 3 minus AF will be equal to square root of 2, which is nothing but 1.414. So 3 minus 1.414 is equal to AF. That is AF is equal to 1.58 value. So even if they are not given in the problems, for the solving of second order low pass and high pass Butterworth filter, the gain will be directly taken as 1.58. Once you know the value of gain, then you can easily calculate, that is AF is equal to 1 plus RF by R1. Once you know the value of gain, then you can easily calculate the remaining resistors RF and R1. So RF by R1 is equal to 1.58 minus 1. So RF is equal to 0.58 into R1. Choose the value of R1, then we can easily calculate the value of RF. For the exam point of view, design steps for the second order high pass as well as for the low pass filters. Use these steps and clearly identify what they asked you to design, whether it may be high pass or low pass. Once again I am telling you, no need to give the gain value for the second order filters, which is directly taken as 1.58 because of the second order Butterworth polynomial s square plus square root of 2 into s plus 1. Your middle term will be equal to 3 minus af. Okay, from this we can easily calculate that value. Okay, introduction to band pass filters. Band pass filters are also called as frequency selectors. Why? Because they pass particular band of frequencies. We all know that the frequency response of the band pass filter is like this. Here we are going to take it as frequency, and here we are considering it as gain, and it should be looks like this. And exactly at the center of the pass band we are going to take it as center frequency FC, okay, which will be taken as AF. And here it is FL, and here we are having it as FH, okay, which is nothing but the frequency response of band pass filter. Band pass filter consists of two stop bands and one pass band. Here it is nothing but pass band, and here it is nothing but stop band. Two stop bands and one pass band. And the bandwidth of the band pass filter will be taken as bandwidth will be equal to FH minus FL, and the center frequency is where the gain is maximum in the pass band region, which is nothing but FC. FC will be taken as square root of FL into FH, and the band pass filter is designed by cascading of the high pass filter and low pass filter. Whenever you are going to design the first order band pass filter, then you have to consider the first order high pass filter and first order low pass filter. Similarly, if you want to design the second order band pass filter, then you have to choose the second order high pass filter and second order low pass filter. And one more important point you have to remember in this case of band pass filter is always FH is greater than FH is greater than FL. And one more thing I want to tell you in case of band pass filter is the center frequency is not exactly at the center in case of band pass filter. That's why we are also calling it as resonant frequency, and the maximum gain of the pass band will be occurred at AFT, which is nothing but the maximum gain that will be occurred at center frequency, and the corner or the cutoff frequencies FL and FHS are at 0.707 into AF, and the bandwidth will be calculated with the help of two corner frequencies, which is nothing but FH minus FL, which is called as bandwidth. This filter is represented in two ways. How can you represent the band pass filter in two ways? Depending upon the quality factor Q or the figure of merit Q, we are going to divide the band pass filter into two ways. If the Q value is less than 10, then you will be treated it as a wide band pass filter. Similarly, if the Q value is greater than 10, then you will be treated it as the narrow band pass filter. Okay, and in case of wide band pass filter, the bandwidth will be very high, whereas in case of narrow band pass filter, the bandwidth will be low. And how can you calculate the quality factor Q? Always the quality factor Q will be calculated as Q is equal to FC divided by bandwidth, and we know the formula for FC and as well as we know the formula for bandwidth. Once we know the formulas, substitute that values, then you can get the value of Q. Depending depending upon the value of Q, we will be conclude that the given band pass filter is the narrow band pass filter or it will be a wide band pass filter. Here I am going to represent the frequency responses for wide band pass filter and narrow band pass filter. First I am going to draw the wide band pass filter and the frequency response should be like this. Here it is nothing but FL and here it is nothing but FH. Both will be at 0.707 into AF. And if you observe this is gain and it is frequency. If you observe this, the frequency for the wide band pass filter will be very high. And similarly, I am going to draw the frequency response for the narrow band pass filter. Okay, while you are going to represent the frequency response, it should be like this. So here it is FL and here we are going to take it as FH, and which will be nothing but the center frequency FC. Okay, if you observe these two frequency responses, the bandwidth will be maximum for the wide band pass filter and the bandwidth will be minimum for the narrow band pass filter, and Q value will be less for the wide band pass filter and Q value will be greater for the narrow band pass filter. And for both the cases, FC will be square root of FL into FH. And one more important point you have to remember is always FH should be greater than FL in case of band pass filter. And while you are going to design the band pass filter, whether it may be the narrow band pass filter or whether it may be the wide band pass filter, always you are going to cascading the low pass filters as well as high pass filter. That means for the designing of one band pass filter, we require one low pass filter and one high pass filter. Combination of those two will be treated as a band pass filter.